Good afternoon. Our team will present our analysis of the Takeo software cataloger business case. Our dataset includes 1,405 customer records and 13 variables. Before building our models, we examined the purchase rate in the data. We found that approximately 51.25% of the customers made a purchase, while 48.75% did not. We also find the mean of Y1 is 107.6128, which we will continue to use in our later analysis. We partitioned the data into training and validation sets with 60-40 split. For each outcome, we excluded the other, so when modeling Y1, we remove Y2 and vice versa. Moving on to our first model, we built a cart regression model to predict Y1, which represents the amount of customer spend in response to the test mailing. We use maximum depth of 3, a minimum bucket size of 20, and a complexity parameter of 0.001. The model's primary split occurs on FRIC, the number of past transactions. Customers with frequency of less than 1 were predicted to spend $0, which aligns with their lack of historical engagement. For customers with frequency greater than or equal to 6, the predicted spending rose significantly to $762, the highest estimate produced by the tree. Customers with FRIC between 3 and 6 were further split based on last update days ago, which indicates how recently the customer record was updated. Within this group, older records had a higher predictive spending of 454 compared to 241 for more recently updated records. In terms of variable importance, FRIC was clearly the most influential, followed by last update days ago. A third variable, address is res, continued slightly but was not part of the final tree structure. For model performance, the RMSE was 143.08, while the average spending across all customers was 107.61. Since the RMSE is greater than the average value, we interpret that this is a sign that while the model captures overall spending trends well, its accuracy in predicting exact dollar amounts for individual customers is more limited.
Then we build a random forest model to predict the customer spending in test mailing. We're using 500 trees, and for each split, the model randomly considered 4 variables as candidates, and we set the minimum terminal node size was set to 5, and finally, the variable importance was enabled to allow assessment of which predictors are most influential in the model. Here for the variable importance here, the random forest model shows that the 3 most important predictors for estimating customer spending. Frequency, the most number of purchases the customer made in the past, is by far the most influential variable. Last updates ago, the number of days since the customer record was last updated ranks second. Address is residential, which indicates whether the customer lives at a residential address, ranks third. These 3 variables provide the core predictive power of the model. The RMSE here is set 136.77. We compare this to the average spending, which is 107.61. The RMSE is greater than the average spending, so this shows poor predictive performance.
Here is an explanation of the parameter values I used in my neural network model for Y1. The model uses 2 hidden layers, with 2 neurons in the first layer and 3 neurons in the second. I selected the resilient backpropagation algorithm with weight backtracking. The model minimizes the sum of square errors during training, which is the standard error function for continuous outcomes like Y1. The model was trained using 2 repetitions. The training process was allowed a maximum of 5,000 steps. Training stops when the partial derivatives of the error function fall below 0.01. Linear output is set to true, which is appropriate for a continuous response variable like Y1. The neural network has 11 input neurons, 2 hidden layers with 2 and 3 neurons respectively, and a single output neuron representing Y1. Each input is connected to both neurons in the first hidden layer, which are in turn fully connected to all 3 neurons in the second layer. The second hidden layer is fully connected to the output layer. The model was trained in 2 repetitions. The variable importance output from the neural network model identifies 3 most influential predictors. Last update days ago, the number of days since the customer record was last updated is the most important variable. US, an indicator for whether the customer resides in the United States, ranks second. Address is resident, an indicator for residential address, follows closely in the 3rd place, implying moderate importance. The RMSE of the neural network regression model on the validation set is 192.13, which is significantly larger than 107.61, the average spending in the dataset. This indicates poor predictive accuracy and suggests that the model may struggle to reliably estimate individual level of spending.
Next, we use a cart classification model to predict Y2, which indicates whether or not a customer made a purchase. This model was built using the same structure as before with a maximum depth of 3, a minimum bucket size of 20, and a complexity parameter of 0.001. The first and most important split in the tree is again based on frequency. Customer with frequency less than 1 were predicted to have 0% probability of purchasing, while those with frequency greater than or equal to 3 had 95% chance of making a purchase, the highest in the model. For customers with frequency between 1 and 3, the model looked at web order, which captures whether the customer placed a web order in the past. Those who had not placed a web order had purchase probability of 46%, while those who had placed a web order had probability of 70. According to the model's variable importance output, frequency was again the most impactful predictor, followed by web order and then last update days ago. These results support the idea that behavioral variables, especially prior transaction frequency and online engagement, are strong signals for purchase likelihood. The model performed well on the validation data. The AUC was 0.817, which was well above the 0.7 threshold often used for indicate strong classification performance. The overall accuracy was 72.6% with sensitivity of 78.6%, meaning the model correctly identified most purchasers. The specificity was 66.7%, indicating fair performance in identifying non-purchasers, and the kappa score was 0.4522, showing moderate agreement between chance, and the p-value was less than 22.2 e to the negative 16, confirming model's performance is statistically significant.
Then we build a random forest to predict Y2 using 500 trees. At each split, the model randomly considered 4 variables as candidates. The minimum terminal node size was set to 5, and finally, the variable importance was enabled to allow assessment of which predictors are most influential in the model. The variable importance output from our random forest model shows the 3 most important predictors for determining whether a customer made a purchase. Frequency, the number of transactions in the past year at the source catalog, is by far the most influential variable. Address is residential. Whether the address is residential is the second most important. Last updates ago, the number of days since the customer record was last updated ranked the third. These 3 variables provide the core predictive power of the model, with frequency being the most dominant one. Here, the ROC curve for the random forest model shows strong predictive performance as the curve rises steeply toward the top left corner. The area on the curve is 0.898, which is well above the 0.7 benchmark, indicating excellent overall classification performance. Here, the confusion matrix evaluates the random forest model using the Uden optimal threshold of 0.455. Sensitivity is 0.775, which meets the 0.7 benchmark. Also, the specificity is 0.86, which is also well above 0.7, indicating the model is very effective at correctly identifying the non-purchasers. So in short, under this threshold, the random forest offers strong overall performance.
For this model, only US frequency, web order, address is residence, source A and source B. In total of 6 predictors are selected. Here's an explanation of the parameter values I used. The model specifies 1 hidden layer with 2 neurons. I used the resilient backpropagation algorithm with weight backtracking. The model minimizes the sum of square errors during training. The logistic activation function was used, which is appropriate for binary classification. The model was trained with 2 repetitions, and the training process was allowed a maximum of 5,000 steps. Training stops when the partial derivatives of the error function fall below 0.1. Linear output is set to false, which is appropriate for binary classification models with binary dependent variable, which is Y2 here. The neural network has 6 input neurons, 2 neurons in a single hidden layer, and 2 output neurons representing purchase and non-purchase. Each input is connected to both hidden neurons, and each hidden neuron is connected to both output neurons, resulting in a total of 12 input to hidden and 4 hidden to output connections. The model is again trained in 2 repetitions. The variable importance output from the neural network model identifies 3 most influential predictors. Fric, the number of transactions in last year at source catalog, is by far the most important variable. Source B, an indicator for source catalog B, ranks second. Web order, an indicator for 1 or more web orders, follows in third place. The ROC curve shows strong classification performance from the neural network model as the curve rises steeply toward the top left corner. The area under the curve is 0.868, well above the 0.7 benchmark, indicating excellent discriminatory ability. The confusion matrix evaluates neural networks classification performance using the Uden optimum threshold of 0.4843. Sensitivity is 0.7589 and specificity is 0.7857. Both metrics exceed 0.7 benchmark, showing balanced and reliable classification.
Thank you.